everybody, in this video we're going to talk about the empirical rule. So take 3 deep breaths and let's make this math easy. Okay, so in our last couple of videos, we've talked about different ways that we can measure how spread out data is. So we learned about the range and the interquartile range, where the range describes the distance between the maximum and the minimum, and the interquartile range describes the distance between the two quartiles. And then the last one we learned about is the standard deviation. And the standard deviation is definitely the hardest one to calculate because there are a lot of steps to it. But it also turns out that it's one of the most useful measures of spread. And the empirical rule is one of the places where we use the standard deviation a lot. So the empirical rule applies whenever you have a data set that's normally distributed. So what it means to be normally distributed is that if you make a histogram of your data set, that the shape of the histogram is going to look similar to this bell curve. And obviously, if you have hundreds or thousands or millions of data points, it will be more likely that the histogram will actually look curvy like that, versus if you only have like 80 data points. It may look a little more blocky, but the idea is if the histogram follows the general shape like this, then if you take the average, so this is the center of the data, and if you take that average and you add a standard deviation for each one of these lines, and also if you subtract them to go down the number line, then the empirical rule says that there's going to be 68% of the data points between these two lines. So let's say, for example, that the average was, I don't know, like a 9 or something like that, and your standard deviation was 2. So if I add 2 to 9, that gives me 11. If I add 2 to that, that gives me 13. And then I have 15 for this last one. And then if I subtract my standard deviation as well, and I get 7 and 5 and 3, the empirical rule basically says that in my data set, there's going to be 68% of my data points that are between 7 and 11. And then there's going to be 95% of my data points that are between 5 and 13. So essentially that's like 2 standard deviations away from the mean. And then the last thing that the empirical rule tells me is if I go 3 standard deviations away from the mean, then 99.7% of my data points will be within that range. So one of the situations in real life where the data set is usually normally distributed is when you take a test. So let's say that there is a math class and the test scores on the final exam were normally distributed with a mean of 78 and a standard deviation of 5. So because the test scores on the exam were normally distributed, that means that the empirical rule will apply. And that basically tells me that my data set is centered around my mean, which is 78. And if I increase by my standard deviation, so 78 plus 5 gives me 83, 83 plus 5 gives me 88, 88 plus 5 gives me 93. And then if I also subtract and I do 78 minus 5, that gives me 73. 73 minus 5 gives me 68. And 68 minus 5 gives me 63. So these are the measurements of these lines here. And that's determined based on the mean, which is where the data is centered around, and then the standard deviation, which describes how spread out the data is. And so once you get those numbers in place, then the empirical rule basically says that 68% of the students' test scores will be between 73% and 83%. And then if you use the second part of the empirical rule, it says that 95% of the test scores will be between 68 and 88. And then the last one says that 99.7% is going to be in this range here. So 99.7% of the test scores will be between 63 and 93. Now there's still some who may be outside of this range because this is not 100% of the data, but it's going to be a very, very small percentage of the data that is left in these tails of the graph. So now let's do an example where we use the empirical rule to interpret different information about a situation. So the mean weight of an African elephant is 12,000 pounds with a standard deviation of 800 pounds. And then we're asked to answer these three questions. So let's set up our normal distribution curve with the information that we've been given. So we know that the mean, or the center of the data, is 12,000 pounds. So that's at the center of my data. And then if I go one standard deviation above that, that's going to be 12,800. If I go one more standard deviation above that, 12,800 plus 800 is going to be 13,600. And then if I go one more standard deviation above that, I get 14,400. Then I also want to subtract my standard deviation to find these lower marks. So I'd say, well, 12,000 minus 800 is going to be 11,200. If I subtract 800 from that, I'm going to get 10,400. And if I subtract 800 from that, that's going to give me 9,600. So on the first question, I'm asked what percentage of elephants weigh between these two numbers. And those two numbers happen to be 2 standard deviations away from the mean. Because if you subtract 2 standard deviations, you get the 10,400. If you add 2 standard deviations, you get the 13,600. So by the empirical rule, I know that the amount of data points that are between those two numbers is 95% of the data. And so since we're talking about elephants here, the percentage of elephants that weigh between those two weights is going to be 95%. Then for the next question, I'm asked what percentage of elephants weigh between these two numbers. So this one is a little bit different because this one is asking me how many elephants, or what percentage of elephants, weigh between these two numbers. And so notice that this number, the 12,800, is 1 standard deviation away from the mean, but the 12,000 is the mean itself. So I'm going to use the empirical rule, which says that the percentage of data points between 11,200 and 12,800 is 68%. However, I don't want to know how many elephants are in that entire range. I just want to know how many elephants are in this range. And luckily, the normal distribution curve is symmetrical. And so basically, that's just going to be half of the 68%. So I'm going to say 68%, split it in half because I'm only looking at the data points between 12,000 and 12,800. And that tells me that the percentage of elephants that weigh between 12,000 and 12,800 is 34%. Then my last question is what percentage of elephants weigh less than 9,600 pounds? So 9,600 pounds is way down here. And basically, I want to know what percentage of elephants weigh less than that. So to figure this one out, I'm going to use the empirical rule that says that the percentage of data points between 9,600 and 14,400 is 99.7. So that's the percentage of data points within that range, which means that the percentage of data points outside of that, so in this range and in this range, is going to be 100% minus 99.7. And so that tells me that there's 0.3% of elephants that are either smaller than 9,600 or heavier than 14,400. And so then I'm going to divide this by 2 because I'm only interested in the elephants that are less than 9,600 pounds. And because the normal distribution is symmetrical, I can just divide it in half so that I get only this part on the left. So if I do 0.3% divided by 2, I end up with 0.15%. and that's the percentage of elephants that weigh less than 9,600 pounds. So that's how you can use the empirical rule. If you have any questions, let me know, and I hope that you guys have a great day.